All right. So my plan today with fifth hour was going to be to start section 4.3, but after talking to them for a few moments, it became pretty clear that not a lot of us had looked at 4.1 and 4.2 yet, which is totally fine. So we're gonna go to 4.4. 4.4 doesn't really depend on what we did on 4.1 or 4.2 or 4.3, so it's a bit of a standalone section, which feels like a good thing to do if nobody's looked at the previous stuff, had a chance to do that yet. Are
we still able to ask questions about homework?
Oh yeah, we can do some questions from 4.1 or 4.2 or whatever. Sure. Let's do that. What do you got, Blake?
Okay, so on 4.2,
okay.
Would you mind doing number 16, please?
4.2, 16. All right. So it says let f of x equal 2 minus the absolute value of 2x minus 1. Show that there is no value c such that f of 3 minus f of 0 equals f prime of c times 3, 0. And asks then why does this not contradict the mean value theorem? Okay. So let's start here by handling the second part first. That sound okay to you, Blake?
Sounds perfect.
Okay. So here in this case, like the mean value theorem says that let f be a function that satisfies the following hypothesis. F is continuous on the... Now let me just screen cap again. Be easier for everybody. We can all see it. Okay. F is continuous on the closed interval AB. So my f of x here is this absolute value function, definitely continuous on that interval. F is differentiable on the open interval AB. Ooh, absolute value function sometimes has an issue with differentiability. So in this case, our A and B are 0 and 3. So if that corner on my absolute value function happens between 0 and 3, we know that that's going to be the hiccup of why the mean value theorem appears to be failing when it's not actually failing. It's because this function is not differentiable somewhere on there. So the easiest probably way to sort that out is just to graph this guy. Mr. Kulik can tell by looking at it, but probably not most of us. And the graph would be a natural way to just look for where that corner is. So I'm just going to graph this over 0, 3. And then I don't really know how big or small this is. I mean, I kind of do, but let's just do normal. And there I see I have the corner in between 0 and 1. So there we go, right away. I feel good as to the second part. Why does it not contradict the mean value theorem?
Because it didn't satisfy.
Yeah, because f of x is not differentiable on 0, 3, or everywhere on 0, 3. So let's settle the first part now. Luke?
If you were to set up a piecewise function for that, would it be x is equal to 1/2 and then x is equal to -1/2?
Greater than and less than, yeah.
Greater than less than.
At positive 1/2 though, right?
Yeah.
If you look at the picture. Yeah.
Okay.
So the way I would look at this is, I mean, Mr. Kulik knows that it's just like a transformation form, like right as the general form. So like when I factor this out, the 2 out, the vertex is like h comma k 1/2, 2 is the vertex. Anyways, to show that this is true, or show that there is no value c, when we're asked to prove that like no such thing exists, what would we do? The easiest way to do this is proof by contradiction. So we'd say, suppose, there exists a C on AB such that f of 3 minus f of 0 equals f prime of C times 3 minus 0. Okay, so f prime of 3, or I'm sorry, f of 3 is 2 times 3 is 6, minus 1 is 5, 2 minus 5 is negative 3. F of 0 is 1. So if that's the case, then the derivative at C needs to equal negative 4/3, right? But if I look at this absolute value function, that was it, right? I copied that right? Okay.
Wait, so why would it be 3 f prime of c, but then it's like f of 3?
Well, 3 minus 0 is just
wait,
3.
that's not okay. I get it.
It's just 3 times f prime. You know what I'm saying? But the derivative, or the function, is this absolute value function, right? That kind of, it looks like this, right? Well, what's the slope on this piece?
Positive.
Well, the slope is constant. It's either this or this, right? You have 2 slopes possible everywhere. Everybody agree? Well, let's see if we can sort that out, what that slope is going to be then. Right? So the slope here is, this is going to be a piecewise function, as Luke kind of indicated, right? Where we've dropped the absolute value and just kept everything else the same. And then we'll negate the absolute value. And this is true when that stuff in the absolute value is positive, and we would negate when the stuff in the absolute value is negative. Everybody okay with that reasoning? So simplifying that stuff down here, I get negative 2x plus 3. And then here I get 2x plus 3. And this is equivalent then for when x is greater than 1/2 and x is less than 1/2. I guess one of them could be or equal to, it doesn't really matter though. So what's the derivative then going to be equal? Well, it's going to be negative 2 when x is greater than a half. It's going to be positive 2 when x is less than a half. And that's a contradiction, right? Because what does the derivative need to be at c? Negative 4/3. Can it be negative 4/3? No, the derivative has to be either 2 or negative 2. Done.
The two arrows.
That's your symbol for a contradiction. Yeah. Yep. Again, that's like fancy mathematics notation, but
Okay, so can you just explain one more time just the final step, like how that contradicts everything?
so if this happens, the derivative at c needs to be negative 4/3. But the only values the derivative can have for f is 2 and negative 2.
Okay.
So it can't happen, right? You can't have negative 4/3 isn't negative 2 or positive 2.
But isn't it in between them? Or does that not matter? Is it just it can only just be the values of negative 2 and positive?
Yes, only those two.
Okay.
Because remember, what does the graph look like?
Yeah.
The graph looks like this. So here the slope is 2. Here the slope is negative 2. Everywhere on the derivative is just one of those two slopes, right?
Uh-huh.
Well, except for the vertex where there's no derivative. But does that feel okay?
Yeah.
Okay. And again, like I did that like really detailed. You could draw a picture and be like, look, the slope over, like the slope here and the slope here is 2 and negative 2. Like nowhere is there a slope other than that. So you can't have a slope of negative 4/3, which is what you would need for that thing to hold true. Is that cool? Did you have another one?
Yeah, if anybody else wants to.
Can we take a look at 31?
In section
4.2.
4.2? Sure.
Yeah, I mean, yeah, that's like, yeah.
You said 31?
Yeah.
Okay. Yeah, another piecewise function here. All right. 31 says let f of x equal 1 over x and g of x equal 1 over x when x is greater than 0 and 1 plus 1 over x when x is less than 0. Suppose that f prime equals g prime for all x in their domain. Can we conclude from corollary 7 that f minus g is constant? Well, what did corollary 7 say? Let's grab that real quick and dump that in here. Wasn't really where I planned on that going, but so corollary 7 says if f prime equals g prime for all x in the interval ab, then f minus g is constant on ab. Thus, f of x is equal to g of x plus c, where c is constant. Okay? Okay, so I see what's gonna, this is not gonna work, or corollary 7 does not apply, and I see why. And the key here is on this interval AB. But we have for all x in their domains, what's their domain going to be? Everything except for 0, right? So if I pick, say, the interval -3, 2, that's not true, right? Corollary 7 wouldn't hold because at 0, they're not equal. They're undefined. So that's the hitch, okay? So even though, like, for x greater than 0, you know, like we have this, and for x less than 0, we have this, we don't have that we don't have that, you know, like on any interval a, b, right? That's the hitch. Blake?
Okay, so I think I did it a different way.
Okay.
But so how I did it was to so I was able to prove that the f prime and g prime were the same.
Oh, it does say show that those are.
Yeah, you just derive it.
Yeah, that, I mean, it's not hard to do that.
Yeah.
You just do the derivatives and.
For the second part, I did it where I just said f minus g, which is 1 over x minus 1 over x, and then 1 over x minus 1 plus 1 over x. Mm-hmm. And then since those are not the same answer, can you also conclude that it's still not a constant?
Oh, I see what you're saying. Yeah, that's basically kind of saying the same thing, right?
Yeah, okay.
That if you have an interval that crosses both pieces of your piecewise,
yeah, then
you're in trouble, right? Because you're getting like an inconsistent value where if f minus g is a different constant, right? One is 0 and the other is 1 or -1 or whatever. Yeah, that I'd say that's fine.
Okay.
It's basically saying the same thing. Jillian.
Would you be able to show us this one, like with two actual graph examples, like a function for f and a function for g? I feel like it's not clicking for me. I don't know if it's.
Well, g is piecewise,
Or g is yes.
which is why it's tricky here. So like here's f of x, right? And then what was it? Hold on a second. Okay. And the blue there is g, or 1/2 of g. So that's, here's like g of x. And then the red is my f of x. If that helps at all, let me do that and get all that junk out of there so it's a little easier a little less busy. Yes, Blake?
Have a chance to be able to use your charger?
Sure. So Jillian, both blue pieces are G.
Yeah.
Let's go over there. It's plugged into that power strip there.
Yes, thank you.
No problem. So that's all that's going on. It's just that this half of the graph is shifted up 1 unit, and the other half is identical. So if you tried to do f minus g, if you're taking something from this side, you get 0 as your constant. If you take something from this side, you're getting 1 as your constant. And the fact that if you pick something an interval that overlaps both sides, that constant is no longer constant, right?
Okay.
Sometimes it's 0 and sometimes it's 1. That's the hang up.
I guess it's hard to see that as being a constant on the left side just because it looks like they're not consistently like displaced from each other.
Yeah,
Why?
each point is, like, if you look at the x though, like the distance is just like 1 unit up.
Yeah.
It's just been shifted or whatever. But that's all that's going on. Does that feel okay?
Yeah, that's good. Thank you.
Sure. Anise?
So we're doing this problem, that's all you have to learn.
Well, I didn't do this part,
Yeah,
but-
for the second part, that's.
but it's not a big deal. Like, you take the derivative of this and you take the derivative of this and you do the derivative of that, and they all will give you the same thing. Right? The second part is, like what we've described here. It's just the answer is no, and this is the issue, is that the domain breaks that some interval a, b, it breaks. So it's not, so that this isn't true. Or, I'm sorry, that this isn't true. Because all you need to pick is some interval that involves 0. And then that's not true anymore. That's the issue. Is that okay? Others? Blake or Luke? Blake?
I could take this one. Would you mind doing number 29?
Same thing. 4-2 still?
Yeah, 4-2.
Okay. So it says that use the mean value theorem to prove this inequality sine A minus sine B is less than or equal to, or I should say absolute value of sine A minus sine B is greater than, or it's less than or equal to the absolute value of A minus B for all A and B. Okay? So let's say let A and B be real numbers such that B is greater than A. Or I'm sorry, let's do less than A, sorry. So for y equals sine x, maybe we'll just say the function sine x. We know it's continuous on BA and also differentiable on BA because sine is continuous. We know that from trigonometry. And we know it's differentiable because it's one of the functions that are classes that we know is differentiable everywhere. So we can apply the mean value theorem. And that says that f of A minus f of B is equal to f prime of C B minus A. Well, we should say that there exists some C on that interval AB such that this is true.
Before we get going too far, can you just explain to me why you chose sine of x?
Well, because it's
just because there's sines.
Yeah.
Yeah. Okay.
yeah, because that's the function that I want. Because what's gonna happen here? This is gonna be my f of A minus f of B and this is going to be my a minus b. Yeah, so that's all I'm just trying to build this out so it looks like the mean value theorem. So I have like sine A minus sine B equals cosine C of A minus B. Okay with that? And if that's true, if I take the absolute value of both sides, that still has to be true. Right? And since this is a product on the right-hand side, I can like break the absolute value piece between those, right? Okay there. Now, what can I say about the value of a cosine? What's the range for cosine? -1 to +1. But this is the absolute value of cosine, so the range here is 0 to 1. So if I get rid of that, then what can I say? So I was multiplying by a number that was less than 1. If I get rid of that, which side is now bigger? The right side, right? If I divide that side only by something that's a number between 0 and 1, that makes that side bigger, right? Unless, what? It was already 0. If it was already 0 to begin with, then it would be equal still. So that's how I got to greater than or equal to.
How can you divide out the cosine?
No. I'm just creating, I want to build this. This is what I want to build, right?
Yeah. Mm-hmm.
So I have this piece and I have this piece, and they're equal as long as I'm multiplying by this cosine C in here.
Yes.
So if I get rid of that cosine C, I divide it only on this side, it's going to make them not equal potentially, unless they're 0. If the two sides are 0, if I divide by cosine, absolute value cosine C, it does nothing and they're still equal. Okay, so that's the or equal to possibility. If I divide by something that's between 0 and 1, it's going to, and that side is not 0, it makes it bigger. So it's always going to, that right side is always going to be bigger or equal to. That's the explanation.
Very genius.
Very clever, right?
So you only put the equal to it that has like something like that 0 value that's equal to cosine.
Yeah, that's basically what I'm saying. Now, realistically, can this equal 0? That would imply A and B were the same point, right? Which, again, or I guess cosine C could be 0, in which case that's fine. Right? Getting rid of it's going to be, that would mean this side was also 0, so getting rid of it means you're going to have something positive over there anyway, so like it's fine. You just can kind of talk through the cases at that point. But getting to this was going to be the key. And then like what happens if I get rid of cosine? And you just kind of step through like 3 cases, right? If both sides were equal to 0, that meant either cosine C was equal to 0 or A minus B was equal to 0. Well, A minus B can't be equal to 0 because you're pulling it from an interval, right? Those are the endpoints of an interval. If they're equal to 0, then the interval is not an interval, it's just a single point, okay? So what if cosine C is 0? Well, if I get rid of it, the left-hand side's still 0, but the A minus B It would have to be a positive number because it's an absolute value. Okay. And then if it's not 0, then cosine b is a number between 0 and 1. And if I divide by a number 0, 1, that's going to make that side bigger. So again, we're good. So just like an explanation, you just have to be careful to kind of cover the cases there. Does that feel okay, Blake?
Yeah.
You probably figured the mean value theorem had to be used somewhere, but like how was I going to build that inequality out of the mean value theorem was the tricky piece. Okay. Let's go and talk about section 4.4 here. We can always circle back and do some more of these questions when you guys come back from break, and everybody's had a chance to look a little bit more at section or chapter or those 4.1 and 4.2 rather than just a handful of us. All right. So in section 4.4, we're going to take a trip back down memory lane to chapter 2. Remember in chapter 2 when we were dealing with limits? Oftentimes we ran into like these indeterminate forms when we were trying to evaluate a limit, where we had like 0 over 0 or infinity over infinity. And there were actually 8 of these indeterminate forms. Is it 8, 1, 2? I should have numbered them, huh? Seven of them. There. That we talked about, that when we were evaluating limit, if you do direct substitution, you get one of these indeterminate forms. You can't say anything about it. Like it doesn't tell you the limit doesn't exist. It doesn't tell you that it's undefined. It doesn't tell you that it's equal to 0 or infinity or something else. It doesn't tell you anything. Like you just can't, that's not a way to get to the solution. Now, way back in chapter 2, we did develop some methods for dealing with this. So for example, if we had the limit as x approaches infinity of x squared minus 1 over 2x squared plus 1. If we tried to do this by direct substitution, if we plug infinity into the top, we get infinity. And we plug infinity in the bottom, we get infinity. So this would be like infinity over infinity, right? If we tried to direct substitute it. Okay, so one of the tricks that we saw way back in chapter 2 is I could go, okay, well, if I multiply the top and bottom of this by 1 over x squared, I get that, right? And now if I kind of push my limit through, I can do that. And what's the limit as x approaches infinity of 1 over x squared? 0, right? It's 1 over huge, which is just 0. So the actual answer here is 1/2. Hi, Katie. Thanks. Jillian, for you. You're welcome. Everybody okay with that? You remember doing that? What if we had something like this? The limit as x approaches infinity, the natural log of x over x minus 1. Again, if I tried direct substitution, the natural log of infinity is infinity. Infinity minus 1, infinity. Infinity over infinity. Okay, problem. If I try to do this again, though, do the same trick I did, does it work? No, because we had that stupid natural log thing going on there. Like, what do I do with that? Right? If I try doing that, I'm just going to end up with infinity over infinity in the numerator, and I haven't really solved anything. Is everybody okay with that? So, what are we going to do? Well, this is the trick. It's called L'Hopital's rule. It says that suppose f and g are differentiable and the derivative of g is not 0 on some open interval I that contains a. So all I need is that those two functions are differentiable on some interval that contains the limit, or the where we're heading to the limit. And then if I have the indeterminate form where we have 0 over 0 or infinity over infinity, then the limit is equal to the limit of the derivatives. Oh. Okay. That we can do. So let's see this in action here. So let's circle back to this guy that we couldn't do anything with. The notation I'm going to use is when I do L'Hopital's rule, I'm just going to write like an H over the equal sign to show that like I'm taking the derivative here. Just so it's a little bit easier for everybody to follow. What's the derivative of the natural log? Over x. What's the derivative of x minus 1? 1. Now let's do our direct substitution. What's the limit as x approaches infinity of 1 over x? 0. What's the limit as x approaches infinity of 1? 1. So my answer here is just 0. Mr. Kulik, where has this been my entire life? What a helpful tool. Now, what's the catch with this? Has to be in the indeterminate form to be able to use this. Okay? If it's not indeterminate, you'll get the wrong answer. It will not help you. Let's do another. First thing we check. Is it indeterminate? Okay. If I do direct substitution, what do I get? Okay, which is just infinity over infinity. Looks good. Let's do it. Indeterminate form. Well, L'Hopital. What's the derivative of e to the x? What's the derivative of x squared? Okay. If I do direct substitution, what do I get? Infinity over infinity. Mr. Kulik, it didn't work. Do it again. What's the derivative of e to the x? Okay. What's the derivative of 2x? 2. If I do direct substitution now, what do I get? Infinity over 2, which is just infinity. What a clarifying process this is. Like nothing tricky going on. I just do derivatives. Mr. Kulik, I can do derivatives. This works. Let's do another one. Okay. First thing I should check is it indeterminate? What do you guys say? It is, right? Log of infinity is infinity. Cube root of infinity is still infinity, right? Okay. So, what's the derivative of the natural log? 1 over x. What's the derivative of x, or the cube root of x? Okay. What do I do now? Let's simplify this, right? Like we just have two different kinds of x's. I'm going to think about the numerator here as x to the negative 1. So that's going to be when I divide by 1/3 is the same as multiplying by 3. Then I'm going to have x to the -1 minus a negative or plus 2/3. That becomes -1/3. So this is really the same thing as the limit as x approaches infinity of 3 over x to the 1/3, which is 0. Yeah, 3 over huge. It's just 0. Mr. Kulik. That's so nice. Teeks.
When you saw like the 1 over x, could you have just known that would it like 1 over x was 0?
The problem is at this point it's 0 over 0 if you sub.
Oh, okay.
Right? Because you have 1 over x to the 2/3 there in the bottom, so it's really 0 over 0 at that point. So you can't actually say that at that point.
Right.
You had to get the x's together in one place before you could make that determination. And I don't mean to be a jerk about it, but like definitely could be a situation where you have like a 1 over x on top and a 1 over x on the bottom, and then they just cancel out and it's not 0. You know what I mean? So like you do have to be pretty careful still.
What if you multiplied by like 1 over x over 1 over x? Or say 1.
So you just want to like multiply by x over x or something here. You could do it that way.
Yeah.
That'll do the same thing. It'll end up right back there. That would be okay. Sure. All right, let's do another example. First thing we should check is it indeterminate? Okay, well, tan of 0, what's that? Does the AP expect you to be able to do that in your head with no calculator? They do. Okay, so think back to the unit circle. In terms of x and y, what is tangent? So y over x, right? At 0 degrees, what is the point on the unit circle at 0 degrees? 1, 0. So tangent is 0 over 1, y over x. So that is 0 minus 0 over 0, so that is indeterminate. Everybody's cool? Okay. So L'Hopital. Derivative of tangent is secant squared. Okay with that? Let's try it again. What's secant of 0? Secant is 1 over x. Nope, at 0, we're at the point 1, 0, so it's secant is 1. So 1 squared minus 1 is 0. Over 0 is still indeterminate. So what should we do? L'Hopital again. What's the derivative of secant squared?
Yeah.
This is a chain rule problem, right?
Oh.
So the derivative f prime of g of x times g prime of x would be 2 times secant times tangent, or 2 secant squared tangent. Let's try direct substitution again. Secant of 0 is 1, tangent of 0 is 0, 2 times 1 times 0 is 0, over 0. Still indeterminate. So what are we going to do again? L'Hopital. Do you really want to do that again? Look at this terrible derivative we're going to have to take.
Anything for an answer?
Well, what was secant squared again when we did the direct substitution?
1.
1. So I'm going to do this instead. Right? Because I remember there was a limit rule that would allow me to do this. And I'm going to reduce along the way. Because that limit's just 1. Right? So 1 times that, that's great. So now I'll do L'Hopital. Because it saves me having to do like a product rule and a chain rule with the derivative, which, I mean, I could do. It's not that big of a deal, but, you know, like, hey, why not, right? Look for the shortcuts, my friends. The derivative of tangent is secant squared. Derivative of 3x is 3. Secant squared of 0 is 1 squared.
Wait, why is that? One. Not less.
Secant squared of 0 is 1. Because secant of 0 is 1. Because cosine of 0 is 1. And secant is 1 over 1. Or 1 over cosine, right? Yeah. Unit circle. Trig. Gotta remember it. Phil.
How did you get rid of the entire secant squared x? Like, where did that go? Oh, just this one. Okay.
So this was a property of limits from back in chapter 2. Is that I can do like the limit of a product is the product of the limits. So that's what I did up here because I could evaluate that part of it.
Okay.
The other pieces gave me the indeterminate part.
Right. Okay. So you can like find the limit of one and then use what we on the other to determine.
Well, then I multiplied that stuff together, right? 1 times that is still, and then I used L'Hopital on the piece that I had that was still indeterminate. Exactly.
Okay. I see. Why did you cross it off and say equals 1? Is that just for plugging in 0? Or oh, that's just for plugging in 0.
It's exactly what we did. We evaluated that limit because it was finite.
Okay.
It was not indeterminate.
That makes sense. So you can evaluate one and then not evaluate the other. Okay.
Yep.
Would that be true if this were like a division problem or something else other than this multiplication situation?
Well, here's the thing with the division. That's what I need it to look like to be able to use L'Hopital. It has to look like a division problem. So I would not want to separate out division pieces, although I could do that. That's not wrong, but I wouldn't want to because I need the division problem to do L'Hopital. John.
What if you wait. No, never mind.
Okay.
I'm trying to think of it. So it is always like a fraction function.
We'll talk about what if I have something that's indeterminate that doesn't look like a fraction. What can I do? Yeah, that's coming. That is coming. All right, so what? L'Hopital this? Sine of pi is?
Is that negative? No, that's a pi approach.
That's pi approaching from the left. Okay. And cosine of pi is? -1. So this is? Which is 0. Note that if you didn't check that at first and you tried to just L'Hopital this, you'd end up with trying to say that's infinity. Oh, sorry. It's negative infinity. But anyways, wrong answer. Right? So if you accidentally L'Hopital something that is not indeterminate, you will get the wrong answer. Okay? All right. So tricks. What about these other 4 or 5 indeterminate forms? Right? What if I have a multiplication problem, like something 0 times infinity? What can I do? Well, if I have like f times g, I can just think about it as f times 1 over g, or g times 1 over f, right? So it doesn't really matter which way you write it. Let's look at an example. So limit as x approaches 0 from the right of x times the natural log of x. Which one do you want to make the 1 over, the x or the natural log?
Sorry, what is it approaching?
0 from the right. What do you guys think? I would do it this way. I don't want any part of that ln as a fraction. Right? That just makes the derivative harder to deal with. If I can make the fraction a polynomial, that I like, because I'm just going to think about that as x to the negative 1. Note that this is, we checked here, 0 times infinity is L'Hopital, right? The natural log of 0 is undefined. We have the asymptote. It's going down to negative infinity there. So it's 0 times negative infinity technically, but like, who gives a poop whether it's positive infinity or negative infinity? So it is indeterminate. We do this. This is now in a form for L'Hopital. We can check again if we want. The natural log of 0 is infinity. 1 over 0 is infinity. We have infinity over infinity, right? So L'Hopital. The natural log of, or the derivative of the natural log is 1 over x. The derivative of x to the negative 1 is going to be negative 1 times x to the negative 2. So again, if I think about that as negative x, I can combine my like terms. So it just turns into negative x. Right? Negative 1 minus a negative 2. When I add the exponents, or subtract the exponents, I guess I should say. And then when I do direct substitution, what do I get? 0. No. All right then. So the goal is we L'Hopital until we can get to direct substitution. Now, if it's a multiplication problem, not a big deal, right? What if we have a subtraction problem, like infinity minus infinity? Well, the goal would be to try to rewrite this as a quotient. Let's look at an example of how we might do that. So limit as x approaches pi over 2 from the left of secant x minus tan x. First thing we should check is it indeterminate? Secant is 1 over x. At pi over 2, that's 0, 1, right? So that'd be 1 over 0. That's infinity. Tangent is sine over cosine. So 1 over 0. That's infinity. Infinity minus infinity. that is indeterminate form. So it says to rewrite this as a quotient. How am I going to do that? I've already told you how to do it. Secant is 1 over cosine. Tangent is sine over cosine. Those have a common denominator. Oh, that was pretty easy. Now it's in the form where we can L'Hopital it. Yay! Derivative of 1 is 0. Derivative of sine is cosine. Derivative of cosine is negative sine. At pi over 2, cosine is 0. At pi over 2, sine is 1. Again, back here, I canceled the negatives, right? Like I didn't write it down, but like who cares? You guys cool? Let's see another one, right? Oh no, I don't have another one. What about the last situation where I have like one of these indeterminate forms that are powers, like 0 to the 0 or 1 to the infinity or infinity to the 0? Well, here's the trick, is that we're going to take our function and rewrite as a product using a natural log. And then we'll go back and evaluate our limit with an exponential. So let's go ahead and take a look here. First thing I should do is check to see that this is one of these indeterminate forms. Sine of 0 is 0, so I have 1 plus 0, so I have 1 to the. Cotangent of 0 is 0 over 1. So that's, oh, I'm sorry, cotangent is cosine over sine. So it's 1 over 0. So this is 1 to the infinity. So this is an indeterminate form. So this is what we do. We're going to take the natural log of both sides. That allows me to move the exponent down to a coefficient. And to write this as a quotient, which is what I want to do to be able to use L'Hopital, I remember that cotangent is probably 1 over tangent would be easier. That way I don't have a product rule in the numerator later on. Right? Not wrong to do what you just said, but I would probably do it this way because it makes the calculus easier a little bit later on. So if I want the limit as x approaches 0 from the right of the limit of the natural log of sine 4x, or 1 plus sine 4x over tan x, that's now in a form I can L'Hopital. So when I do the derivative of the natural log of 1 plus sine 4x, what do I get there? 1 over 1 plus sine 4x times it's a chain rule, guys. Good. Times, it's a chain rule, guys, 4 over secant squared. Okay. Let's do our direct substitution here, see if we need to do L'Hopital again. Sine of 0 is 0. Cosine of 0 is 1. So the top is not 0, so I'm, at this point, feel pretty good about not L'Hopitaling again. Secant of 0 was 1. So we get 4 here. But we're not done, because we didn't find the limit. We didn't find this limit. We found the limit for the natural log of y. So here's all we have to do to finish. That limit is the limit of y is the same thing as e to the ln of y, right? So that's e to the limit of ln y, which is just 4. So we have e to the 4th. Jillian?
Can you explain this step that you took, before, when you had like all the limits up at the top?
Mm-hmm. So this stuff here, I just called y.
Okay.
So that is the same thing as e to the ln y, because the ln and e just cancel each other out,
Oh.
right?
Okay.
And the reason I wanted to do that is because I already knew what the limit of the natural log of y is. That's what we did down below.
Right. Okay.
So then I could just substitute that number in, and then we're done. All right. We got one more example, and then we'll call it good for today. Sound good to you guys? Okay. Sure. Sure. Okay, so obviously this is 0 to the 0, right? As an indeterminate form, that's easy to see right away. Okay. So I'm going to call x to the x. I'm going to call that y. So we do the natural log of y. So what's the natural log of x to the x? X times the natural log of x. Okay? So the limit, as x approaches 0 from the right, of x times the natural log of x. That's not in the form for L'Hopital, though, so I need to rewrite that. What was the trick I used when I have two things being multiplied?
Over x.
Yeah. So I'm going to do the natural log on top, and I'll do 1 over x on bottom. And really 1 over x I'm going to think as x to the negative 1. Because I'm going to L'Hopital that. And it just makes the derivative easier to do that way. So the derivative for the natural log of x is 1 over x. The derivative of x to the negative 1 is negative 1 x to the negative 2. So those x's, if I think about the numerator as x to the negative 1, the denominator is negative x to the negative 2. That simplifies down to just negative x. which when I do direct substitution is 0. Yes. So, well, this is the limit of the natural log of y. So if I want this, then this is the limit as x approaches 0 of e to the natural log of y, which is going to be e to the 0, which is just 1.
Are you putting the x to the left side?
So I got right here, I have this over this. So that's going to be negative 1, x to the negative 1 minus a negative 2, which is negative 1x to the first. I just use my exponent rules and simplified. Is that, do you see it, Anise? Okay. Here. So that's what I had. So I just simplified using my exponent rules. And that's how I got the negative x. Does that feel good? Okay. So let's talk about due dates on stuff, right? So looking at things, maybe 2 or 3 of us have started the chapter 4 stuff at this point, correct? That's probably about right. So my thoughts would be is I'm not looking for any chapter 4 stuff done until the 27th. The 17th? Oh, no, that's wrong then. I set it for, what did I set the due date? That's not the right date then. Well, no, I probably did at one point, but like, what did I actually put in the calendar here? That's not right. Oh, yeah, I did put it on the 27th. Is that not the right day? Edit details. Yeah, let's put it on the 4th. Okay. Just FYI, I had to do something different with where I list the problems for this one because I ran out of like characters that I could name it. So this one was just called 4.1, 4.2, 4.4, and if you look at the description, there the problems are listed. I couldn't list all the problems in the name because I ran out of characters. I was limited to 255 and I ran out of characters. I know. But here's the thing. Would you rather like just a big assignment due later than like something you have to scramble to try to get to that nobody's even looked at yet? Right? Like that's not fair. Like just, there's going to be something big later. So nothing due on Sunday. Nothing due the Sunday you come back. If you're not caught up on things, if you're like mega behind in chapter 3, get caught up over break. If you haven't touched chapter 4 yet, get caught up over break. If you're in a good spot where it's like, yeah, I just have to kind of put some, do a couple from 4.1 and 4.2 and then like finish this 4.4 stuff, you probably don't even really need to really do anything. But because you're that far, if you're that caught up, you're a maniac and you're for sure going to look at stuff over break, which is great. Blake's not the only maniac in here. There's other maniacs that just don't let everyone else know that they're a maniac. Blake just doesn't care. Right?
I am getting community time. He's crazy out 4-4.
Reminder again, what happens tomorrow? More time on test. Okay?
Okay.
As for the finishing out the semester, me trying to look at days, I don't know that it's going to be a great idea to try to cram another chapter 4 test in before the final. At this point, I'd be leaning towards the chapter 4 stuff is just going to be on the final. So just to let you guys, give you a heads up there that this chapter 3 test we're doing is probably going to be the last test for the semester, because I don't think it's a great idea to have like this exam for chapter 4 and then like 4 days later be talking about having a final. Just seems kind of dumb to me. But we can talk about that more when we get back from break. Amanda?
Do you know how you like do your final?
Nope.
Okay.
I don't
That
yet.
should be like a first semester out of trig.
Blake.
Algebra review, that's what I really need.
Yeah, for real.
Like, if you go over, like, it's just like all like trig identities, and like, that would actually probably be more beneficial to me. I'm serious.
I
I
understand.
had to like you can leave a blank unit circle and I have to fill that in. I'm serious.
I understand.
I need like a big sheet of all the laws of math.
Blake.
So do you know how long these the actual exam periods are supposed to be? Are they 80 or 90 minutes?
I'm not sure.
Okay.
I'm not sure.
But for this class,
There's a lot of uncertainty.
Yeah, it's one of those things like I haven't even sat down really hard and thought about like what I want to do, but I know that I need to do something different than I've done on the test because I've overshot the test length on 2 out of the 3 occasions. So I need to, for the final, like there's not a extra do-over for Mr. Kulik there. If he screws that up, it just becomes a big mess. So I need to make sure that however I write this is something that's going to be doable in the allotted time, which makes me hesitant to like recycle questions from before that clearly took a long time. So we'll talk more about the format once I've had some time to really sit down and think carefully about like what I want to do.
The December problem.
It is a December problem. That's the anesist thing I could have said. John.
Right now,
Yeah.
like, would you be leaning more towards like a lot of faster problems, or like just a few problems from each chapter that take a really long time?
I would lean towards like probably trying to split the difference and have like half of the time's worth of questions be quickies, and then like one that'll be time consuming from each of these 3 chapters we've covered that are like kind of hits on a couple of different skills that are not necessarily like quick things, but you have to kind of put some skills together similar to what you'll have to do on an AP test is kind of what I'd like to think. It'd be like 10 quickies and then like 3 longies is kind of what I was envisioning in my head. You know, where it's like, here's 10 questions that are like 4 minutes a pop, and here's 3 questions that are more like 10 minutes a pop, and that's like 70 minutes worth of questions, which is, if we have 80 or 90 minutes, is probably about right to not run over, is what I would be thinking in my head right now. It's a question of like sitting down and like being careful about that and making sure that none of those 4-minute questions that I have my mind on are actually like a 15-minute question, or at least are like, if you approach them the right way, are all like, okay, that was quick. Which, guys, ideally, the front page of what I gave you guys should have been quick if you did them the right way. Should have been quick.
So I like.
I know. I looked at what I papered, like thumbed through what some of us were doing, I'm like, whoa. That was not the easy way of doing that. But Luke.
So I like